The broadcast is now starting. All attendees are in listen-only mode.
Hi everybody, this is Rocky Dunlap from the Earth System Modeling Framework. We'll get started in just a few minutes. Looks like we've got 2 or 3 minutes before the top of the hour. Thanks for joining us for this tutorial. I want to point your attention, if you're already on the line, to this link at the bottom. This link was also in the email that I sent out. If you have questions that you would like to ask during the tutorial, this is a link to a Google Doc that everybody can edit. So we just ask that you put your questions on there, and we'll try to answer those in between the different sections we're going to cover. So we'll get started in just a couple minutes. Okay, we're at 2 past the hour, so I think we'll go ahead and get started. In case you just joined in the last 2 minutes or so, I wanted to point out the link at the bottom to the Google Doc where we're collecting questions. So during the tutorial, if you could just type any questions that you have on there, we'll try to cover them to the best that we can. And my name is Rocky Dunlap. Also on the line is Bob Umke. Bob is the grid representation and ESMF regridding primary developer and expert on all those things. So he's going to keep an eye on the question sheet as we go and help us answer questions as we go along. So the topics that we'll cover during the webinar today are first an overview of the Earth System Modeling Framework and some of the applications that are using ESMF. The ESMF grids and regridding section, which is about our parallel interpolation engine. And finally, the NUOPC interoperability layer, which is a layer on top of ESMF that coupled modeling applications are using to facilitate sharing of components across different modeling applications and across different agencies in the US. So ESMF was initiated about 15 years ago as a multi-agency response to calls for common modeling infrastructure. And what ESMF has is a set of component interfaces and high-performance utilities. And there are several different ways that you'll see at the bottom left in the box there. There's multiple different ways to use ESMF. One way, if you're building a coupled model, and so you want to put together multiple modeling components, ESMF provides a lot of utilities and communication infrastructure for putting together these components in a parallel environment. It can also be used kind of like you would use a regular library, any software library. So you can pick and choose some of the functionality in ESMF and bring it into a model. Offline, you can use ESMF to generate interpolation weights between model grids. And you can also access this same interpolation weight generator through a Python package called ESMPy. Some of the metrics on the right, ESMF is now very mature software. We test on a lot of supercomputer platforms throughout the US nightly. We have a large number of people on the mailing list and our support lists that we communicate with regularly to continue to improve the software. We have about 10 developers that are actively working on ESMF right now and making and preparing for releases. And our latest release was an internal release at 7.0, and we expect in the next few months to have a 7.1 release out. But the date for that hasn't officially been set yet. I also mentioned NUOPC. This stands for the National Unified Operational Prediction Capability, and it is a software layer that sits directly on top of ESMF, and it uses the basic ESMF component constructs, but provides a set of generic components. So essentially these add more power to ESMF because the generic components have some built-in behaviors. And we'll go into more detail in the last section about NUOPC and what the different generic components do. But as new people are adopting ESMF, we are encouraging folks to take a good look at NUOPC because there are a lot of components, a lot of model components out there that have these NUOPC interfaces. So some of the applications that are currently using ESMF I've listed here. The one on the left is called NIMS. This is the NOAA Environmental Modeling System. And this is an infrastructure layer used at NOAA that is designed for all of their next generation modeling applications. And so this is a common infrastructure that supports multiple coupled models. It's the global model, regional model, hurricane tracking. Essentially, the idea of this is to provide this common infrastructure layer. And at the heart of it is NUOPC compliant components, such as a mediator capable of connecting different model components together. With the U.S. Navy, they are also using ESMF and NUOPC. Two of their major systems are COAMPS, which is a regional forecast system, and NavGem, which is their global system. They have some specialized coupling needs which we're able to support, including nested domains and nest-to-nest coupling. So if that's the kind of capabilities you need, you should definitely consider looking into ESMF, and we can give some more details about how the nesting works. At NASA, the GEOS 5 model and data assimilation system and the Model E climate model are using ESMF. One thing that's interesting about the GEOS model is there's a large number of components. So they have broken out their atmosphere model into dynamics and physics as separate components. And then within the physics, they have further broken down all of the different parameterizations that are involved in a physics package have all been broken up into ESMF components. And these are all organized into a deep hierarchy. The advantage of this is it is more straightforward to switch out individual pieces of the physics by putting in a new component, since they are sharing this ESMF interface layer. And then another system I'll mention is the Community Earth System model at NCAR. They have been using ESMF for a while and have recently decided to adopt the NUOPC layer for increased interoperability of both within CESM and also the ability to integrate components from outside NCAR into that model. You may be wondering, which kinds of model components are out there that are already using ESMF and have NUOPC interfaces. So we have put together a directory called the Earth System Prediction Suite. The link for this is at the bottom, and this is only a part of the full listing available on that site. But essentially, this is a set of atmosphere, ocean, land surface, wave, hydrology, I think are the main models that we have out there that already have NUOPC coupling interfaces. And the reason this is an advantage is it allows these components to move more easily between applications. So as an example, the HICOM ocean model, which is the first item under the ocean models there, has been set up as a NUOPC component, and it's being used in the NOAA-NIM system, the Navy global system, and at NCAR in the CESM climate model. And we're reusing the same coupling interface for all of those. So when we talk about component interfaces, this is the standard subroutine signature that ESMF defines. And so you can see the code there on the left. The parameter list for the initialize, run, and finalize routines always looks like this. The first parameter is comp, which is a pointer to the component itself. This is similar to the self parameter if you're familiar with Python object-oriented programming. The second parameter is the import state, and then the next one is the export state, and these are for the incoming and outgoing coupling fields. There's a clock, which is your model timekeeper, and then a return code. Now, this kind of interface is designed to coexist with whatever native model subroutines and infrastructure code that you already have. So if you adopt ESMF, you're not required to extensively refactor code or really change much about the internal of the model. Instead, you just think about wrapping the topmost layer of your model with a set of subroutines that have this signature. And that is essentially what's required to take a Fortran model code and turn it into an ESMF or NUOPC component. we do get a lot of questions about, okay, what is the overhead of doing this if we decide to adopt ESMF? So we have a performance page where we've collected a lot of overhead numbers. One in particular I've linked here is the 2010 study we did with in-car for the CCSM4 model, and it showed that the component overhead was around 3% or less. And then even more recent than that, we have begun measuring the overhead of NUOPC components. And I've linked at the bottom here a new report about NUOPC overhead, so you can follow that link and look at some of the numbers for basically what is the cost to you of implementing your model as a NUOPC component versus not having any NUOPC and just making direct calls. Our general performance philosophy is, first of all, to do no harm. So I mentioned before that the component interface overhead is very small. We have measured this a little while ago at about 55 microseconds. Of course, this depends on the particular processor platform you're running on. More recently, that has actually gone down a little bit on more modern processors, but it's a very fast call through. And we have a set of prototype codes that show that if you have accelerator optimizations, open MP threading, or other kinds of very specific optimizations that you've implemented in your model, ESMF does not get in the way of those and does not disturb those. So we essentially try to stay out of the way and allow your optimizations to continue to work in the same way that they always have. Scalability is very important. We test to thousands of processors on a regular basis. Our customers test even farther out than we do. So, for example, NASA, I think, regularly tests out to 30,000 processors for some of our key parallel methods, such as the sparse matrix multiply. With respect to task parallelism, a nice part about the component interface is it gives you a level of task parallelism. It introduces that into your code. So, for example, this would allow you to run an atmosphere and an ocean component. If you had an atmosphere-ocean coupled system, you can run those in the same MPI world, essentially, but run them concurrently. And so at every component interface, you now have this option of introducing this level of concurrency into the model itself. The third item here is preserving locality. So you have a lot of options essentially in how you connect and communicate between components. I guess the most optimized way, if you set it up this way, is to actually directly share references between components. So clearly this requires that the components would be on the same grid, for example, and have the same parallel decomposition. But if that is the case, ESMF will allow you to, and NUOPC will allow you to pass pointers. You can also do local memory-to-memory copies if you're sharing the same grid and decomposition. Now, if you have your components, let's say they're running concurrently, so you have assigned a disjoint set of processors to each component, then you will obviously need to do some communication between those components, and that's where the redistribution and parallel grid remapping come into play. So the link at the bottom then is the full listing of the performance reports that we've done. So if you're interested in some specific numbers, I would encourage you to follow that link. The parallel programming model in ESMF is based on a construct we have called the VM. And this is an abstraction of the hardware layer. So the VM, instead of talking about MPI tasks or P threads or any kind of specific implementation, we talk about PETs in ESMF, which is a persistent execution thread. And these PETs are mapped to the lower level library. So often PETs are mapped to MPI tasks. but we do maintain this abstraction level to give more flexibility to the application. There is flexible mapping to resources. So you can assign, of the full global set of pets available to an application, you can assign subsets of those to certain components. And that's how, for example, you would get concurrent execution of components. One newer thing that we're looking at now is extending the VM to recognize heterogeneous resources. And we now have prototypes where this is working. The idea here is if you have a code, let's say you have a coupled system and one of the components can take advantage of an accelerator device like a GPU, you want to make sure that you're mapping those components to the hardware in a smart way such that the components that can take advantage of GPUs are on those hardware nodes. And this is important. There's a lot of heterogeneity in modern supercomputing platforms. So not every node will have access to every kind of accelerator device, for example. So you have to intelligently map out your full set of pets to the hardware. And that's the purpose of adding these new abstractions to the VM. So to communicate between components, we use this concept called a state. So each component has an import state and an export state. The states are containers for other ESMF data types, such as the field object. So typically you will, when you're building a coupled system, you will put a set of fields into the import state that you expect a model to bring in from another model component. The metadata about these fields travels with the field themselves. That includes the name of the field, what the underlying grid structure is, the coordinates associated with each of the points on the field, and the memory layout in parallel. And since ESMF has all this metadata, it is now able to handle the data transfer between components. And this is really one of the, I think, most powerful parts about ESMF is the different parallel communication options. Really simplifies your life over trying to write these things from scratch using MPI calls. All that is abstracted and hidden from you. So you won't see necessarily a lot of MPI calls when you're using the ESMF library. So the communication operations that are supported are listed here. Most of these are based on the fundamental operation, which is a sparse matrix multiply, which applies coefficients or weights fully in parallel to distributed data. So the matrix is distributed across the set of pets that you're running the application on. The sparse matrix multiply has an auto-tuning feature which automatically kicks in and essentially tries several send-receive combinations at the beginning and times those to set up an optimal performance route. And so the other operations then, most of them can be defined as a sparse matrix multiply. So the redistribution is essentially changing parallel distributions, but it's not changing any of the values. There's no interpolation involved here. So for example, you could take a field that's distributed in one way on M pets and distribute it in a different way on N pets. And ESMF would make sure the field is reassembled correctly on the other side. Scatter gather, again, is a special case of that, where you're either coming from or going to one pet. Within a model, we support a halo operation. This fills in the ghost cells around a local region that a process owns with values from the neighboring processor. And that's obviously required for a lot of numerical algorithms. When you're cycling through the I's, J's, and K's, and you need to get your neighbor values in order to compute the cells that you own. And then finally, the regrid operation moves a physical field from a source model, grid, or mesh to a destination grid or mesh. And then in the second part, we'll talk about the different kinds of grids and meshes that we support. And in order to use the regrid, you will have to provide ESMF with the grid structure and the coordinates associated with each of the points. So there's a lot there. If you have questions, there's a few resources here that will be helpful for you. Most things are linked off the ESMF homepage, so that's a good place to start. We have a reference manual, which is really good. It's very comprehensive, so all of the public APIs are documented in detail, and there are also example codes in there showing how to use each of the APIs. The user's guide has the installation procedure and some architectural overview of how ESMF works. And then the link at the bottom is to a bunch of example applications that you can download and compile and run, and that's a good way to get started. Excuse me. The installation procedure is straightforward. I've given you kind of the very short version in the code snippet to the left. You're essentially setting up your environment with the compiler you want to use, the implementation of MPI, and then make, check, make, install. If you're working on some of the bigger systems in the national labs, likely ESMF has already been installed, and so if you look through the modules there, you might be able to use a pre-installed ESMF. Not a lot of requirements. You need a Fortran and C++ compiler, MPI, CPP, make, and Perl. And there are a few optional dependencies. If you have, for example, a netcdf installation, that will allow you to read and write ESMF fields to netcdf files. Finally, the support list is very important. If you have any technical questions, general questions, or feature requests, we do keep a close eye on this list. If you email the list, all of the developers receive the message, and we try to be very responsive to that list. So that's a good starting point. So that was the kind of the overview part and application part. So I'll switch over to the questions and see if we have any questions on there, which hopefully I can help with, or maybe Bob.
So we have a question. Do you know, I haven't dealt much with AdCirc. Do you know if they have an ESMF interface?
AdCirc does at NOAA. I know they have built a NUOPC interface, and they're coupling that with WaveWatch 3. And I think that's in development right now, but they have developed the NUOPC interface.
Okay, so I'll just say yes. Yes, it does.
And we'd like to be in touch with the developers. Maybe a message to ESMF support, and we could try to link people together.
Couple to WaveWatch 3. Okay. And then we have someone who's having audio difficulties.
Okay.
And I emailed Karen, and she said that they could try you can try the computer audio. They're having difficulties on the phone.
Okay.
And then there's a question about, is the coupling between models based on a time step basis? For example, a time step in a hydrological model will transfer data to a groundwater model and wait until the ground model completes its time step and provide the data back.
Yeah.
And so yes, you can set things up to operate on set things up in that way between two models where it runs for a time step and transfer data and waits to transfer data back, right? But you can set things up in a more complex way too, right? Where you can have several models at once and running through time steps and going between each other concurrently.
Right. That's right. And different coupling frequencies as well. We have examples of codes that say have faster processes which couple more frequently and slower processes which couple less frequently. So that would be supported in the same application. And this is a good example because we have an application with the hydrology community where we have a land surface model coupled to a hydrology model, and it's working essentially the way that this question is written, where the land surface takes a time step and sends its surface states, such as the soil moisture content and runoff, to the hydrology model. The hydrology model routes the water around through channels and updates the soil moisture and ponded water on the surface, and then passes that back to the land surface model, which then updates its state. And then that just happens iteratively for the entire forecast. So it works very much like this question is described. Okay. So it looks like that was all the questions. So I'll go ahead on to the next part. And those are really good questions. So please keep them coming. So the next part is about ESMF grids and regridding. So the fundamental kind of grid structures that we support are what we call first the grid, which is a structured representation. So if you have a logically rectangular tile or a set of tiles that are connected, then we consider that a grid. We have an unstructured representation called a mesh. And then the third option is a location stream, and this is a set of disconnected points. So you don't really have a grid structure, but you have a set of points and they have coordinates associated with them. For example, if you have a set of observations coming in. So these are some different aspects of the regridding. As I said before, we always have high performance in mind. So the interpolation weight matrix, calculating that, which is kind of the fundamental operation here, is done completely in parallel in 3D space. So if you provide, for example, if you have a 2D surface and you provide lat long coordinates, we're going to project that onto a 3D Cartesian space and do all of the weight calculation there in parallel, and that helps to avoid issues that could come up at the pole singularity. There's a wide range of supported grids, logically rectangular and unstructured grids in 2D and 3D. The observational data streams, we can handle both global and regional grids, and we can go between them. And then the coordinates supported are both Cartesian and spherical coordinates. Now, when you've defined two grids and you want to map between them, you have a choice of how you would like ESMF to perform the interpolation. So there's a list of interpolation methods there. Some of them are conservative and some of them are non-conservative. So that's a choice that you make depending on what the physical quantity that you're remapping. You can decide how you want to do the interpolation. And then there's a lot of other options as well. I don't have them all listed, but important ones. One really important one is masking. So if you provide ESMF with a land sea mask on one or both sides of one or two of the grid that you want to transfer between, ESMF will respect the mask, for example, and not use points that you've masked out in the calculation of the interpolation weights. So how do you actually use the regridding? There are these three ways. Online, during a model run, we have the Fortran API. Offline, you can use either Python to generate the weights and apply the weights, or a few file-based command line utilities that we have that operate over netcdf files. The regrid operation is fundamentally, we have it defined in two stages. The first one is the computation of the weight matrix. And if you look at the code snippet here, you'll see that there's a call to ESMF field regrid store. The store call is the call where the weight matrix is computed, and that matrix plus communication information between MPI tasks is all stored in the route handle, this route handle object. It's a ESMF defined data type. So that actually, the store doesn't perform the interpolation. When it's time to perform the interpolation, you make a call to ESMF field regrid, and you pass in your source and destination fields and that route handle, and it's going to efficiently reuse the pre-computed weights and communication pattern to apply. Essentially, it does a sparse matrix multiply. And then at the end, when your model run is over, the ESMF field regrid release at the bottom frees up all the resources. So this is a typical pattern you will see if you're using ESMF online to regrid between model components, between grids and different model components. The same kind of pattern here where you have a store call and then you do the operation and then a release call is used for the redistribution and for the halo operation. So that's kind of the typical pattern that you'll see. So the Python interface is called ESMPy, and there's a link to the homepage there where you can see how to download the package. We do have it available in some of the Python package managers, so it's easy to install. It does link against the ESMF, Fortran, and C library behind the scenes. So this is just providing a language interface into the same regridding capabilities supported by ESMF. And the Python capability is also a parallel capability. And then for the file-based regridding, in our last release, we have these two command line utilities which are installed with ESMF. The first one is ESMF regrid weight gen, and this reads in 2 netcdf grid files and then outputs a third file that has the interpolation weights. The output format is using a widely known and used format called script. And so you can then take that weight file and essentially do with it what you want. I mean, you can read that in and apply the weights. And so that's just giving you the weights on the left. And there's some options to the command line argument for what kind of interpolation you want to do and whether it's global or regional grids that you're working with. And then on the right, this both generates the weights and applies them from a source to a destination grid file. So if you have grid files that have, excuse me, if you have grid files that have data in them, you can use this to do both the calculation of the weights and the regridding. And so you have to provide the names of the source and destination variables that you want to regrid. So these are the non-conservative methods. I think the standard method, kind of the workhorse method, is the bilinear option. So in this case, the destination value, so for any particular point, it's just a linear combination of this on the source grid, the source points that are surrounding that destination value. And so that's weights are applied based on the distance of each of those source cells to the destination cell. And this would typically be used to regrid model state variables such as a temperature field or wind speed. Another non-conservative option is higher order patch recovery. This is a second order method, and it is more expensive because we're going to use more surrounding source points to compute the weights. But the result is you will get a smoother result in the destination field compared to the bilinear. So you would make a trade-off there between the cost of it and the quality of the interpolation between the first two. The final option for the non-conservative is a nearest neighbor option. This will either map the nearest source point to a destination or the nearest destination to a source. And this often is useful for making sure, for example, that all of the destination points are mapped to. Sometimes we'll use the nearest neighbor also as a kind of extrapolation in conjunction with the other methods. So for example, maybe you apply a bilinear interpolation, but because the masks maybe are slightly different between the grids, you may have some points in the destination which are still unmapped. And this might happen, for example, along a coastline. The nearest neighbor could then be used to fill in some of those, to fill in all of those unmapped values on the destination side to assure that you have a full field and you don't have any holes or any gaps. Another reason to use the nearest neighbor might be categorical data, where you have a set of discrete values, such as land surface types. So you really don't want an interpolation. It wouldn't make any sense in that case, but you just want to choose from a discrete set of points, a set of options. So the nearest neighbor works well for that. Okay, on the conservative side, the first order conservative method is available right now and has been in ESMF for a while. We use the overlapping areas to weight the source values that are coming in. And by doing that, it preserves the integral of the field across the interpolation. So if you're moving a flux or something across a boundary, and conservation is essential, then you would choose the first order conservative method. Now the quality of the interpolation is good, but it will likely have higher error because we're trying to conserve than the bilinear, for example. So you're trading off the conservation for the error in this case. And then a new method which is not available yet, but which is coming in the 7.1 release, and we have initial results for, is a second order conservative. So this uses a wider stencil than the first order, so it is more expensive. It still preserves the integral of the field, but it's going to give a smoother result than the first order. I think we have an example. Yeah, so here's an example of the first order versus the second order conservative. So you can see the field, the analytic field is much smoother in the case of the second order on the bottom right. Here is a performance chart showing the different regridding interpolation options scaling out to 16,000 processors. So we do test this pretty regularly to make sure that we're scaling on to the number of cores that our customers need. So this is one example of kind of the performance numbers that are available on that on the ESMF performance link that I showed you previously. So let's look a little bit more at kind of the code and what the different data types are that you need to work with to use the ESMF regridding and parallel communication. At the bottom, there's a class called the dist grid, which is a distributed index space. So you just think of defining your index space, your i's, j's, and k's kind of globally, and then the dist grid uses something called the DE layout to map that index space to a set of processors. In the middle, the geometric types are the ones that I mentioned, the grid, the mesh, the log stream. There's a fourth one that I haven't mentioned yet, which is called the X grid or the exchange grid. This is a special kind of grid which is made up of it's kind of a super grid made up of the combination of multiple source grids. And this was a method designed by GFDL in their climate model, which is now being used in multiple other institutions. And it's a way to ensure conservation, for example, at the surface, between the atmosphere and the surface. So that is a specialized type of grid which we support in ESMF, the exchange grid. And then when you've defined the geometric type, at the top, there's the field class, which is a representation of a physical field in a model. Okay, and so because this field is connected to the grid or the mesh, we're able to pull out the coordinates associated with each of the physical fields to do the remapping. When you're defining a grid using the Fortran API, we provide a number of, let's say, convenience APIs depending on what kind of grid you're trying to create. So I've provided some of them at the bottom. So if you have, for example, a periodic dimension, we will preset up the connectivity for you using this grid create one peri-dim option. And so you really would need to look, depending on the kind of grid you need to create and what options you want to support. If you look at the reference manual, you'll see a large number of ESMF grid create options there. One of the more recent types of grids that we support is a multi-tile grid, such as a cube sphere. And there's actually there's a couple different ways to represent a cube sphere in ESMF. One is through the unstructured mesh, in which case your data fields will be 1D. And then because the mesh is used for the interpolation weight calculation, this will be slightly more efficient if you use the mesh, because we can skip the step of essentially converting the grid to a mesh. The downside is you would have to work in 1D. If your model code is set up to work over 2D space, then the second option might be appealing, which is a multi-tile grid. So in this case, a cube sphere is made up of 6 tiles with certain connectivity between the tiles. When you have the cube sphere set up, either as a mesh or a grid, you can then use the regridding to go to and from the cube sphere to other grids. And then at the bottom, you can see the 3 main APIs that are involved with creating cube spheres. The decomposition options are flexible in ESMF. The top example shows kind of a regular decomposition. So the picture is kind of, let's say, your full domain, and you're running, and you want to basically chop it up into 6 decomposition elements or DEs. You can actually have ESMF do that for you and just say, break this up into a 2x3 kind of overlay grid, and that's that reg decomp argument. 2x3 gives you this DE layout. You can also provide specific counts in each dimension in order to do irregular decompositions. And you can provide, at this note here at the bottom, completely arbitrary DE blocks. So a lot of times we work with codes, they already have a decomposition set up, and it may be for particular performance reasons. So ESMF will just adopt whatever decomposition that you have set up. You don't have to use any particular decomposition that ESMF enforces. One thing that's important to know is there's a difference between a decomposition element and a PET. And this provides a lot of basically an additional layer of flexibility, because you can map DEs to PETs however you want. The typical case is you will divide up your domain into the number of decomposition elements it's the same as the number of PETs, and have a one-to-one mapping. That's kind of the standard operating procedure. However, there may be a reason to allocate multiple DEs per PET. So for example, this would allow OpenMP threading to operate over different DEs within the same PET. When you've defined the grid or the mesh using the API, the next step is to create a field object. So this code snippet on the right is showing first the creation of the grid object, and then the creation of a field on the grid. So the first parameter here is the grid itself. In this case, we are asking ESMF to allocate memory because we're providing a type kind here. Some of the other options are whether you want the indexing to be local to the DE and always start over at 1, 1, 1, 1, 1, 1, 1 in the lower corner, or whether you want the indices to be global. And then the stagger location is also something that you can set depending on where in the cell the field data actually lives. So you could set it at the center or in the corner or on one of the edges. Now, after you create the field, you now have a distributed object and memory has been allocated for it. So you will need to get on any given pet the set of local bounds that pet is responsible for. And so using this called a field get, we can get the lower and upper bounds and then do the computation over that part of the domain. So the mesh creation API allows you to provide all of the nodes and coordinates required for either a 2D or a 3D mesh. If it's a 2D mesh, you can have any number of sides on the polygons. It's limited only by the computer memory. And then in 3D, the elements need to be either tetrahedra or hexahedra. And the coordinates that you can provide for the mesh, they can be either Cartesian coordinates or spherical coordinates. And then the mesh, like the grid and the field and everything else, is a fully parallel distributed object. So each pet will own part of the mesh. So the call at the bottom is showing how you explicitly create a mesh by providing a set of nodes and then how they're connected together into elements. We can also, in addition to creating kind of from scratch from the API or from parameters, there are some netcdf file formats that we support both for the grid and the mesh. There's the script format, which we support both for the grid and the mesh. GFDL, in order to support multi-tile grids, has a representation called grid spec, which we can read in and again create either a grid or a mesh out of that. For example, a set of netcdf files can be used to create a cube sphere grid. UGrid is a proposed extension to the CF metadata, and it supports unstructured grids. So we can read this in and create an ESMF mesh. And then we also have a kind of our own format, a custom format, which is efficient for specifically representing the ESMF mesh class. The supported regrid options, if you're going between 2D grids, all of the different regrid options and interpolation methods are supported. There are a few limitations if you're going between 3D grids and meshes. The best way to see if a particular combination is supported is to go to our website, which I've linked right here. The supported regrid combinations for each release will tell you whether that's something that we've tested and is supported. So some of the recent and upcoming updates with respect to regridding. Regridding to a location stream is supported now. Multi-polygon regridding. This means you could treat a polygon that's disconnected. Say, for example, a cluster of islands can be represented as a single grid cell. So you can map to and from it, and it'll have a constant kind of value over that set of disjoint polygons. The new cube sphere APIs are available in development snapshots now if you need it, and will be released with the 7.1. And another thing is the per location status output. What this allows you to do, the per location means after I do a regrid operation, I could go through each of the destination cells and understand, was that cell mapped to, and if it wasn't mapped to, why not? So maybe it wasn't mapped to because the source was masked out, so it didn't have enough source points to do a meaningful interpolation to that destination. This allows you then, as the user, to make a choice. What do you want to do with the unmasked cells? Oh, I'm sorry, the unmapped cells. Okay, things that are scheduled for the upcoming release is the second order conservative, an extrapolation option, dynamic masking. So the masking I mentioned before is completely static. It's set before you compute the interpolation weight matrix. So if you have a mass that is changing over time, say ice is melting, and so a point that used to be ice is no longer ice, you need to change that mass dynamically. So that's a new feature which will be supported in this upcoming release. And then reading multi-tile grids from the GFDL grid spec format will be part of 7.1. Okay, let's go over to the questions, see if we had any.
So the first question we had is, the second order conservative will be available in the next release. Can you give a more concrete time frame for that? So I believe that we're currently expecting the next release to come out sometime at the end of this year to early the next. That's what you said at the beginning of the talk, right, Rocky?
Yes. Yeah.
But then once the second order is finished, which should be very, very soon, you can get a development snapshot for that. And if you want that, you should send us email to our support list, ESMF_support@list.wc.noaa.gov, then we can try to get you one of those as soon as it's available. The next question we had is, can you use ESMF regrid weightgen on HDF files? So currently ESMF regrid weightgen, the file formats that we support are all based on netcdf. But if this question is, but then netcdf4 is, you can use HDF5 compression underneath. So if the question is if we support that HDF5 compression, we do, but you have to pass in the netcdf4 flag to get that, to be able to use the netcdf4 files. Another question we had was, in the file-based approach using ESMF regrid weightgen, what approach do you suggest if you need some fields interpolated using bilinear and some using conservative? And so what I said is you should run the ESMF regrid weightgen once to do the bilinear weights, the second time to do the conservative, and then you can just read in that weight file and apply the weights as often as you'd like for the bilinear weights, and the same thing for the conservative. You can just read in the weights and apply them as much as you'd like. And then we have a new question. As hydrologists, we use GIS data sets quite a bit to demarcate the boundaries of our models. Does ESMF provide support for GIS data sets like networks, polygons, polylines, etc.? So we don't provide direct support right now. However, we have done some interpolation of GIS, of hydrological catchment data sets. And we have a tool that converts from one of the polygon formats into UGrid or some of the formats we support, like UGrid or ESMF unstructured format, and then from there you can use the regridding tool. So if you're interested in doing this, I would email ESMF support and we can help you out, because I believe we still have some of those tools sitting around that'll let you do, they're not in the ESMF repository right now, but we have them in I think Contrib that we could use to help you convert your data files to one that we support.
Yep.
Why did you choose Fortran ESMF? That's a good question. So this decision was made before I joined the project, but probably the best answer I can say is that most of the models that we deal with are in Fortran, and so that's the most convenient interface for the people using ESMF to use. Underneath, ESMF is written in C++, and we actually, as Rocky mentioned before, we do have a C interface and a Python interface, so if you need to interact with it in one of those languages, you can. But I guess the best answer for why we chose Fortran is because that's what all the models we were dealing with back in the early 2000s were written in. Do you have anything to add, Rocky?
That makes sense. The only thing I wanted to add back to the previous question about the GIS data sets, Ben on our team did some nice work. I mean, as Bob mentioned, he did some nice work in Python. He was working with the NHD plus catchments, which is a database of catchments for the whole United States, continental United States. And he was able to represent that as an ESMF mesh and regrid a kind of what was it? It was kind of it was just a logical
it was
thing, like a represent to the mesh, right?
Yeah, I think it was like a 300-meter, continental United States grid, like you said, uniform lat long to catchment, the NHD plus catchment database. So
yeah,
it was quite a huge. Both of them were huge files, but we were able to do the regridding in a fairly timely manner on one of the supercomputers. So if you're interested in doing this, please contact us, and we can help you get your files. Set up some kind of workflow to convert your files to a format that we have.
Great. Okay, we'll go ahead over to the final section then. Thanks, Bob. Okay, so the NUOPC layer is the last part of the tutorial today. One thing I mentioned before is that NUOPC has a set of generic components. These are different kinds of components. So if you think about ESMF component as kind of a raw building block that doesn't have a lot of predefined behavior, the NUOPC components are kinds of ESMF component that have predefined behavior. And that's based on the role of the component in the coupled system. So the driver is the main locus of control, and what you'll be doing is plugging in as children some of these other components. So a driver could have 2 or 3 models as its children, and will coordinate the execution of those components. And I'll show you how you specify the run sequence is is parameterized for the driver. So we'll show you how to specify that. Okay, the yellow is a model which is a wrapper for a geophysical code, like an atmosphere model or a hydrology model. And we use the word cap often to describe the wrapper or the layer that sits on top of the model code and basically translates between native memory layouts and grids and clocks and all those data structures which are already set up in the model. We need a common representation of those, the standard set of data types, in order to couple these things together interoperably. So that cap, we put all of that translation layer into a cap, and those NUOPC sees those as individual models. The green arrow is a connector. The connector performs standard communication between models and also between models and mediators. The connector is kind of used out of the box. In a sense, you can customize it to have very specific behavior, but often you want a standard operation like a bilinear regrid, a conservative regrid, a redistribution, reference sharing. So all of those options are pre-built into the connector. And so you can kind of drop a connector in at the point where you need communication. Okay, the mediator is where you would put custom coupling code that occurs at the intersection of multiple models that are trying to communicate with each other. This may be, some people call this a coupler or a flux coupler. You can do things like accumulation and averaging in here. If you're working with several different components that are coupled together, and let's say some of them are coupled at a higher frequency than others, then you will likely want to accumulate some of these, say, fluxes that are coming out and make sure that the full accumulated flux is passed to some of the models that are coupling more slowly. You may need to take an average for certain kinds of fields. You may need to merge a field. So if your surface is divided up into multiple different kinds, so if you have an ocean, ice, and land surface model, and they are all generating a heat flux in a slightly different way, and you want to put all of that together onto a common field and pass that over to the atmosphere, then you need to do all these manipulations somewhere. And it doesn't make sense to try to do that in any individual component, because then you're adding kind of custom behavior for a specific coupling setup in those components. So instead, if we provide this mediator where all of that kind of custom coupling code can go, that helps the other components remain independent. So here's a couple of different architecture diagrams showing different NUOPC configurations. The one on the left, it has an atmosphere and ocean code in it with connectors providing essentially a two-way feedback loop. And then there's a more sophisticated one on the right with 4 different model components and a mediator in the middle. The connectors, again, are used to communicate between the model components and the mediator. So that's going to move your physical fields from these components into the mediator space. So the mediator can perform computation on it, and then the mediator can pass it back out. This is kind of a hub and spoke setup. For the ocean model, one thing I'm showing there is that hierarchies are allowed and supported. So if you have an ocean code that within it has some submodels, they may also be NUOPC compliant and communicate between those components. But from the top level, for example, the mediator sees one ocean component and does not need to be aware that there's a hierarchy of components underneath the ocean. So that allows you to build more complex systems from smaller pieces. So the driver is typically the top level component, and it is the run sequence in it is parameterized. So this is an advantage because you don't need to hard code any particular execution sequence, and it means that you can change this run sequence at runtime by changing a configuration file such as this one. So this is an example from the NEMS system, from NEMS, the NOAA Environmental Modeling System. And so you can see this configuration file has a run sequence here. There's a time step indicator, there's actually a couple of them, which is how for each pass through this run sequence, how far forward would you like each of the components to integrate in time. So at the end of this outer loop, all of these components will have progressed 1,800 seconds into the forecast. And again, the loops can be nested. So here you have a faster loop here. So the atmosphere-ice interaction is a faster process, and so there's communication happening between the atmosphere and the ice through the mediator every 600 seconds. So you actually get 3 repetitions of this loop for every one of the outer loop. So the driver will read this in during initialization and set up this run sequence. Hopefully it's fairly self-explanatory what each of the lines is. So the ocean, atmosphere, and ice are asking those models to advance forward in time. The red is the mediator. One thing that we're showing here is that each of these components can have multiple run phases. This is important for the mediator because every time you execute the mediator, it's doing something a little bit different. So here, this mid phase prep ocean is doing some preparation to the ocean fields in the mediator before calling the mediator to ocean connector and then calling the ocean. So there are these different phases: prep the ice, prep the atmosphere, and so each of those can be distinguished in the run sequence, and they have different run methods inside the mediator, and you can have as many of those as you want. The remap method equals option here allows you in the run sequence to customize the behavior of the connector. So instead of doing a regrid here, we're doing a redistribution between all of the components, ocean, atmosphere, and ice in the mediator. The reason we're doing a redistribution in this case is because the mediator is actually has a copy of each of the grids between each of these components. And you can't tell that from looking at this run sequence, but just to motivate why we're doing a redistribution operation is because we're moving from between components that have the same grid. In this particular system, interpolation between grids is actually happening inside the mediator. So you can't see that here. So anyway, this is what a typical run sequence would look like. And so there's a lot of flexibility in how you specify that. And you don't need to recompile the driver to make any changes to this. In NUOPC, there are different options for both explicit and implicit coupling. So by explicit coupling, it is depicted by this first picture here on the left, where at a regular interval, the components are exchanging data with each other. Now, sometimes you have a situation where one component needs information from a model at one time step, or could be potentially more time steps ahead, so you have this lagged configuration. So NUOPC supports this by by having control of the clocks. You can let one of these components, such as the atmosphere, run ahead and pass back at t+1 to the ocean T. And you can also set up different timescales here, where you have this component at the bottom that is communicating much less frequently than these top two components. And all this comes down to how you set up the run sequence and also how you check the clocks inside the NUOPC caps. Concurrency is supported in NUOPC. This is by making sure that you assign disjoint sets of pets to the components controlled by the driver. So this picture on the left is an example of concurrent execution of atmosphere and ocean. In the case where you have some overlapping pets, that will force the run sequence to be sequential. So obviously these pets here, these ocean pets, can't proceed until the atmosphere completes its computation. So this is not an ideal setup here, because notice that there's some pets here that are ocean pets, which are actually idle, waiting on the atmosphere to complete. So care must be taken in setting up your pet, what we call the pet list, which is how these pets are assigned, to make sure that you get concurrency where you want it, and that you get a sequential execution where you want it, and you have a good load balance situation. So these are just some aspects about NUOPC that are important. There's a single entry point into all NUOPC components called set services. And this is a registration phase that we call right before we initialize the whole system. So this registers all the subroutines in a model with NUOPC. NUOPC uses only the ESMF distributed data types. There's a field dictionary that's provided with NUOPC. And the way the coupling exchanges are set up is by matching standard names. So for each of the physical fields in your code, you'll need to provide a standard name for it. A component on the other side that needs to receive that field will also provide the same standard name, and NUOPC will automatically set up the connections. Now, the initial field dictionary that we have in there is based off of the CF standard names. However, we do work with a number of communities that don't necessarily use CF, so we provided a way to extend this field dictionary so you can add a set of standard names yourself to that dictionary, and NUOPC will be happy and won't complain that you haven't used a standard name. There is a standard initialization sequence that NUOPC goes through. And it helps to identify and link the coupling fields across models, synchronize the clocks, and make sure that all of the components participating in the coupled run have their initial conditions set up. And all this is done in a standard way so that NUOPC kind of knows what to expect from each model during each initialization phase. There's a standard run sequence, which we looked at. I showed you how you specify a run sequence. And then finally, for the build, there's a certain makefile fragment format that we describe, where if you provide, it's basically a list of kind of build dependencies, what libraries are you dependent on. We aggregate all of the makefile dependence fragments from all of the components, and we use those to build the one final executable that is the full coupled system. So this is just a mechanism to kind of simplify the build process, because eventually you need to wind up with one executable. So you have to deal with, how do we build these components separately as libraries, and how do we make sure we got everything linked together in the end. This is a kind of a picture of what we call a NUOPC cap. So at the bottom, think about this as your physical model code. This is your Fortran code base. And you have written the code in certain ways. You know, you've allocated memory in certain ways and certain distributions. You have some way of keeping track of model time. And you have some subroutines that do various initializations and execute the model. Everybody does that however they want, based on the model that they're working with. So the cap sits on top of that and provides a common interface to all of these. So however you've laid out your physical field arrays will be wrapped as fields, ESMF fields, and put into the import and export state. And however you've represented your grid will be wrapped as an ESMF grid. And all the way down, and even the way that you're initializing the model and advancing the model are represented in the cap with different subroutines. Once we have that, as well as the clock, so once we have all of that at the cap level, we can plug that cap into a driver and other parts of NUOPC infrastructure. And so data, the control flows top down in this case. So there will be a call into the cap. Eventually the cap will call down into your model code. This is the reason I said that that ESMF and NUOPC are not invasive. Notice that you really don't need to make a lot of changes. Sometimes we have to change a few things, but you don't really need to make a lot of changes into your physical model code in order to put this cap on top. So that cap is implemented typically as a Fortran module. It may be in one file, it may be in a couple of files. The cap specializes the generic model with details of the particular model. That's basically the wrappers I was talking about that wrap your model data types. And then inside the cap, there is a set of these subroutines, which we have specific labels for each of them, and they provide certain parts of the initialization and certain parts of the model run. So this is just an example of some of the subroutines that would be in a cap. If you have a component and you're thinking about making it NUOPC compliant, these are some things that you should do before you build the cap. First, it's good to have your code basically divided into initialize, run, and finalize subroutines. And that's because the control flow is top down. So we need to be able to call into your model's subroutines at the right time that NUOPC expects those things to happen. It is also good to go ahead and, instead of building an executable, which you would often do, you would typically do if in a standalone run, instead build this code as a library, and that will allow it to be linked to in a bigger system. With respect to MPI, if you have a code that's using MPI WorldCom, because you're typically using the full set of MPI tasks, you'll need to make a slight change there and allow the MPI communicator to be passed in. And in this case, if in a coupled model, you may be running on a subset of MPI tasks. So you can't rely on the WorldCom anymore. And then as far as testing, preparing to test the cap, the way we do this is run, say, a low resolution case of the standalone model, produce some baselines, then put the cap on and put a NUOPC driver on top of it, and drive your model using NUOPC. Now, because that's only changing really the control flow at the top levels, you should not see any changes in the model answers. So our goal is bit-for-bit reproducibility of a baseline run. This gives you confidence that the cap is not changing the behavior of your model in any way. It's just providing this interface. Some resources to get help with NUOPC. We have a how-to document which describes kind of a step-by-step process for making a existing Fortran code NUOPC compliant. There's the reference manual with all the APIs. There's also example caps that are already out there. So here I've linked to the Los Alamos CI code. So this is on GitHub, and it's a working cap that's been being used in NIMS. So you can look at that code, and there's also documentation associated with it. The NUOPC website is linked here, and one other resource I think is really nice that one of our team members has built is a set of prototype codes that are kind of show how the NUOPC infrastructure works, but with dummy models. And this is nice because they're small codes. You can kind of see this picture here. They're small codes. You can download them, compile them, and build them, and really look through how the cap is working, what the driver's doing, but not have to worry about the full code bulk of a real model. And this is also a good way to start by looking at the prototypes, because you can likely find a prototype that has an architecture in it that is similar to what you want to build. So if it's a two-component coupled system, we have an example of that. Or if there's a mediator involved, we have an example of that. There's also a few tools that I'll just quickly mention. There's a compliance checker. This is built into NUOPC. All you have to do is turn on an environment variable, and it will write out verbose compliance diagnostics into the log files. And if it will flag warnings if it sees something that looks like it may not be NUOPC compliant. And it's also helpful for debugging because it gives a lot of information about the internals of what NUOPC is doing. There's another command line tool called the Component Explorer. What it is it's a generic driver that you can link to a single NUOPC component. Okay, such as let's say you've built a cap for your model component, and now you want to test it. Well, you need a driver because the cap is not a driver. So you could use the Component Explorer as a generic driver. It will link to your model and then go through the initialization sequence and try to go through the run sequence. And that essentially lets you test out this code. And it prints out, to standard out, some information such as, okay, here's all the import and export fields that I found in this component. The last tool is called Cupid. It's a plugin for the Eclipse graphical development environment. With Cupid, there's a few different capabilities that are supported. One of the main ones is automatic code generation. So we noticed that a lot of the cap code has a lot of boilerplate code. And so we built into Eclipse a way to automatically generate at least templates and parts of the subroutines that you would have in a cap. We also have some performance analysis capabilities that are supported. So ESMF, that has a tracing feature, if you turn on the tracing feature, it will collect high precision timing of the various phases of execution of NUOPC and ESMF components. I think I have an example here where you can look at what different pets are doing during the execution and see the timings by stacking them together. So this is an example of a trace of a coupled atmosphere-ocean application in NIMS. And this way of viewing the trace allows you to see what is happening concurrently. So you'll notice that this pet at the bottom, pet 270, it's actually executing a different set of components concurrently with these pets above. So this will be helpful in seeing, for example, if you have a load imbalance, you'll see blocking. You'll see a lot of time, for example, waiting in a connector down here because a component above hasn't completed. So that was the set of tools that that we provide for working with NUOPC. So that was the main content we wanted to cover. Let's go back and just see if we have any questions for this last section.
So let's see. Oh, so they asked if there are any specific examples to couple two models, such as WRF and HICOM. And I pointed them to the NUOPC prototypes that you mentioned before.
Okay.
Okay, and then I said, if they might be able to contact someone with a similar coupled system if it's publicly available and they could take a look. So one question is, I didn't know, do you think we can run the GEOS 5 data assimilation framework on NUOPC?
Okay, yeah, I can address that. We have a project right now with GMAO. We're working with some folks there on bringing NUOPC into GEOS. GEOS right now is based on a layer called Maple. And Maple existed before NUOPC, but what's interesting about Maple is it's also based on ESMF like NUOPC is. So at the end of the day, there is kind of this common layer of ESMF components. And what we're doing in this project is to try to unify Maple and NUOPC, and we're actually adding capabilities to NUOPC that Maple supports, because there's a lot of nice things that Maple does, like the hierarchy support that NUOPC is still kind of coming into. The goal of that work would be to be able to have interoperability between Maple and NUOPC, and even have GEOS and all of the components as fully compliant NUOPC components. That is not the case right now. Instead, we're working with a small prototype. We're working with the GEOS CTM chemical transport model to prototype NUOPC in that. As far as running that with Cupid, we have run the performance, the tracing and the performance numbers with GEOS, and you can look at that with Cupid. So if you want some more details about that, if you would just email ESMF support, I can show you how we did that.
And then the next question was, typically WRF needs several pre-processing steps, which we do manually for ESMF. For ESMF, do we need to write a script to automate the WRF run? So I just said that if the pre-processing steps happen just once before you run WRF, then you should be able to just do it before the coupled system using WRF, right?
Mm-hmm.
Unless for some reason that you need to restart WRF over and over inside the coupled system.
Right. Yeah, I agree. The pre-processing is usually unchanged, because when you get to NUOPC, you're really just getting into the forecast. I don't know if there would be a need to read in, restart files during the run. But typically, anyway, it doesn't require changing the preprocessing.
Yeah. Okay, and that was, then there's another question that just came up. Should we have to install Perl on Cupid? I'm not sure what that.
I guess maybe the question is Perl a prerequisite for Cupid, and it's not.
Oh, I guess.
Eclipse is, and Eclipse uses Java. So what you need is Java 8, and then you can download Eclipse. And then when you download Eclipse, you go to the marketplace and you can look up Cupid, and it will install it. So you don't need Perl. Okay, Bob, do you think that's all the questions?
Yeah, that's all I see. So.
Okay. Well, I guess before we go, the last thing I will just, again, because we haven't plugged in enough, the support list, if you have questions. And the final thing is there's a short feedback form here, which we would really appreciate any comments that you have. It really only takes 2 minutes. It's very short. It's a Google form to let us know what you thought about this tutorial. And if there are other topics that you felt like were important that we didn't cover, it would be very helpful to hear that. So we'd appreciate your feedback at this URL here. So I just want to thank everybody for attending. We look forward to working with everybody here. Let us know if you have any questions, and we'll see you next time.